There we go. You guys still see the screen?
Yeah, we can see it.
And you see the slideshow right there, the importance of capacity control. Is that what you're looking at?
Yeah.
Okay. All right, good. Okay, so okay, back to it. So anyway, we're going to talk a little bit about compression ratios and capacity, some of the different capacity control means that you're going to see out on compressors. So compression ratio is pretty self-explanatory, and to figure out what your compression ratio is running, it's just your head pressure in PSI absolute divided by the suction pressure in PSI absolute. And then there's several different things that'll cause your compression ratio to vary. One of the most obvious is a low load. So when you start restricting the amount of refrigerant the compressor is seeing, the suction pressure drops. Now, typically the condensing side is going to stay up high or higher than normal. It's not going to change near as much because the conditions outside don't change near as much as what they can on an evaporator load. And so therefore your discharge pressure tends to stay the same, where your suction pressure will drop much more drastically in relation to that, which dynamically changes your compression ratio. And that begins to add, or it will change the amount of heat that the compressor is effectively producing or removing and transferring. So what we do typically in the field to maintain and to keep the compression ratio in an ideal range is we use capacity control. So capacity control can be done several different, there it goes. So capacity control is basically matching the compressor's capacity to the existing load. So whenever the load drops, we're going to reduce the compressor's efficiency or change its ability to pump the prescribed amount of gas that it can do. So we're just going to reduce its ability to move as much as what it normally does. One of those is to use an unloader, which blocks the suction ports, preventing the piston from effectively pumping any gas. It's not the same as shutting off the compressor suction, where the piston is still going to not pull anything, but it's going to compress something. It actually will disengage the cylinder from operating. The gas just kind of goes back and forth between the suction and the discharge reeds, essentially running it in a neutral position. So we're going to look at some slides here that would be an example for just like a 30 horse, a big 6-cylinder compressor, where we have 3 walk-ins, and as each, you'll see in a minute in the animation, as each thermostat satisfied, we drop out a portion of the compressor to maintain its ability to pump the amount of refrigerant necessary to maintain the load. So here we'll see we got 3 evaporator rooms and 1 compressor going through the condenser, and this is operating at full capacity. So we'll see, we watch the little discharge gas flow up and feed all 3 liquid line solenoids. Suction is going to come out from all 3 evaporators, return back to the compressor. So that's under full load. The compressor is running its matched CFM for keeping all 3 evaporators satisfied, full of refrigerant, and everything good. So all the cylinders are loaded, everything's going according to plan. Now, what happens next is we're going to satisfy one of the evaporators and effectively reduce the load on the compressor. So the suction pressure is now going to drop because the compressor pistons are all pumping the same amount of gas, or trying to anyway. But what we do instead of reducing the amount of flow that is going through the compressor, which effectively changes its compression ratio, and also drops the evap pressure and changes a whole bunch of other things, which we won't get into right now. We're going to shut off cylinder head number 1. And so by disengaging cylinder 1, that what was, and we'll just use arbitrary numbers, what was a 30 horse compressor now becomes a 20 horse compressor. And the suction is maintained, the conditions are now maintained for the 2 running evaporators as opposed to all 3. As we further decrease load, we'll see here what happens if we shut off evaporator number 2. That's going to stop that flow and even further reduce the compressor's necessary capacity. And so that in there will then de-energize or disengage cylinder head number 3, and now turning that compressor, that 30 horse compressor, into a 10 horsepower compressor. So now the cylinders that are active are only what is necessary to maintain 1 of the 3 walk-ins. And then the final stage would be when evaporator number 3 shuts down, and now we have no refrigerant flow. And so now the low pressure switch is just going to shut the compressor off completely, as there's no need anymore for any refrigerant flow whatsoever. So that would be the staging of a unloader, a compressor with multiple unloads. So now we're going to show a little bit of a detail of the Copeland and Carlyle unloaders and loaded and unloaded states. So you can kind of see a little bit of the internal flow of what's going on and how Copeland differs from Carlyle. Effectively, no matter what compressor manufacturer you have, they're all effectively doing the same thing. They just have their own way of doing it. So here's is showing the compressor head cutaway of a Copeland compressor fully loaded. So the coil unloader coil on top is de-energized. The suction port is open, and the unloader piston is backseated. So basically all the refrigerant suction is going to come in through the suction into the cylinder, and the piston's going to pull down, pull the gas in, suction valve opens, discharge gas opens when the piston comes up, and we have our flow through the piston and cylinder. So the compressor is fully doing its full load of work as the piston operates. So now we're going to show what happens when we unload or effectively shut off the piston, allowing the compressor to still run, but this one piston now, which is usually one of 3 or more if it's a bigger one. But anyway, let's see what happens when we want to unload. So we're going to energize the unloader solenoid up top, which draws its piston up, and it's effectively going to activate this bypass piston, the sub-assembly piston that's in here. The little piston drops down, and now discharge gas is allowed to push the unloader piston out of the way, because the pressure on the discharge side is going to push it out and down, which shuts off the suction port. So now suction gas cannot reach the piston. And then it's effectively, since now there's no more new refrigerant running into the piston doesn't have anything to compress. The discharge valve is going to close because the pressure in there is much higher than it is on the suction side. And just by the nature and the physics of the reed valves acting as check valves, the discharge, as long as your valves seat properly, the discharge pressure will stay on the discharge side and not enter the suction side. And then the suction pressure low side, obviously, the discharge not going to enter into it and blow into the suction. Now, one of the things you can find in the field is when a compressor is unloaded, if it's running abnormally hot whilst it's in unloaded mode, you probably most likely have either a bleeding discharge solenoid, discharge reed, or sometimes your unloader piston doesn't seat all the way, and a small amount of suction is being pulled into the cylinder, and the compressor is doing a minute amount of compression and working. And so if you encounter a compressor unloader or an unloaded compressor that is running abnormally hot while unloaded, you usually have a mechanical deficiency inside of the head. So that's something to be aware of. Okay, let's move on and we'll see what goes on inside of a Carlyle. So here's a Carlyle, and it's just like the Copeland, but their valve structure and their valving and the effective mechanics inside are just a little bit different. So with a Carlyle running fully loaded, we have the same components. Cylinder, the unloader solenoid is de-energized, so it defaults to fully loaded operation. Unloader piston is back seated. So Carlyle uses the discharge gas to keep the piston pushed down, where Copeland actually uses the discharge pressure to activate the cylinder, or to deactivate the cylinder. So we can see the pressure flow in the piston, just like normal, from the suction side into the piston, out the discharge side. And then the discharge pressure is used to hold the piston, the unloader piston, out of the way, thus allowing suction gas to flow. So the discharge pressure on a Carlyle loads the unloader valve, if that makes sense. So if you see in this drawing, you'll see how the unloader piston up there in gold is actually pushed out of the way by the discharge pressure. So here now we're going to see the unloaded stage of a Carlyle. So what's going to happen when we energize our solenoid coil here, we see that the discharge pressure is going to close, which now opens and allows the piston, which at the unloader piston, there's a big spring underneath the unloader piston. And that spring now is going to overcome the suction pressure. It's much stronger than the suction pressure differential is. And it's going to then push that piston closed and stop the flow of suction into the cylinder. So mechanically, we have a spring to activate and move a piston and thus shut off the suction flow into the cylinder. So you see here we have a blocked suction passage. So now we can no longer receive any new refrigerant gas into the piston for it to do its job. So since there's nothing there for it to pump, the suction valve is going to close, discharge valve is going to close, and the piston just basically runs in neutral. It's not doing any work. That does produce a small amount of friction, you know, the piston running up and down, but the mass of the cylinder head and the activity of the other pistons right next to it running generally keep it cool. So the only heat that should be produced from an unloaded piston is from friction. So moving on, let's talk again about the discharge temperature of what happens when we start changing our compression ratio. So the compression ratio again is the PSI absolute divided by the discharge, the head pressure, absolute head pressure divided by the absolute suction pressure. And as the suction pressure decreases, the compression ratio increases. Now that's assuming right now, that's assuming that the discharge pressure is staying relatively steady, so that if the discharge pressure drops relative to the suction pressure, obviously your compression ratio stays kind of the same. But in this scenario, we're going to assume that the discharge pressure is staying relatively close to saturated condensing because the load that happens to be changing is on the suction side and not on the discharge side. So as our compression ratio increases, the discharge vapor temperatures are going to increase. So you guys are all aware, I hope you're all aware of, you know, the harder you compress a gas, the more heat is produced. The more activity you create in those molecules, the harder you press it, the harder you squish the gas, the more temperature is produced. So high compression ratio equates to high discharge temperatures. So in a compressor, here we've got just a little blurb here. The maximum compression ratio you're ever going to really see or want to see is 12 to 1. Depending on what type of oil your system has, oil will start to smoke or burn at around 300 degrees Fahrenheit. And that is not a good scenario you want to start producing inside of the cylinder head. So we'll look, R22 is notorious for this. It's kind of it's a hotter temperature gas, and it produces a lot of heat when it's compressed at high ratios. So if we look at an R22 system used for air conditioning, where we've got the evap temperature is around 40 degrees, we're going to assume we're at a compression ratio of 3.3 to 1. The discharge temperature is roughly, we'll say, around 175 degrees Fahrenheit. That same compressor, if we apply it to a low temperature, where the evaporator is now minus 20 as opposed to plus 40, we run a calculated compression ratio of 11 to 1, and the discharge temperature now goes from 175 to 280. That same compressor, if we go for ultra low or extra low temperature, where we're running minus 40, we end up with an 18 to 1 discharge, or 18 to 1 compression ratio, where our discharge temperature can reach 320 degrees. Copeland's maximum discharge for Copeland, their maximum discharge pressure measured 6 inches from the compressor is around 225. So that scenario, trying to run that compressor at minus 40 with a 175 discharge is way above its operating envelope. Carlyle is around 250. You can go a little hotter on Carlyle than you can on Copeland. Hopefully that kind of makes sense for everybody. Here's a little visual chart. It's not sharing that screen anymore. You get this slideshow. Anyway, here's a little chart here showing that visually, and to kind of put it into perspective when we're showing the same thing but with pressures rather than just temperatures. So here we're running a 275 psi absolute discharge pressure, liquid pressure, which condensing temperature is around 120. And we can't really change that because the outside ambient is what it is, so that's as low as we can go, because the nature of the physics behind condensing. So for an AC application here, we got 40 degree evap temp. The evap pressure for this is running 83 psi with 175 degree discharge temperature at a 3.3 to 1 compression ratio. So here we'll see our evap temperature. Our suction vapor temperature entering the compressor is at 60 degrees. Let me move my window thing out of here. And then the compressor discharge temperature at 175, where it crosses over the saturated condensing temperature. Again, for the freezer at minus 20 with a 25 psi evaporator, Same discharge temperature. Compression ratio is 11:1. And the 60-degree evaporator entering temperature at 275 psi is now 280, and the minus 40 is now running the discharge at 320 degrees, which, as we mentioned, is unacceptable. So what do we do when we want to run a compressor in, what do we do when we need to, to have a low temperature application? What do we do when we have to have a minus 40 or minus 30 evaporator temp and a compressor in this scenario, and we know that we're going to run into that scenario? Well, what we have is what we call demand cooling, and it's used on some single stage compressors, but for the low temperature applications where you got one compressor and a few different loads, and with that low suction and where our high head temperatures we're going to get, we put a sensor inside of the cylinder head that is going to activate a solenoid valve. That solenoid valve is going to inject refrigerant into the suction line of the compressor and thus increase its mass flow and lower the temperature. If you increase the amount of gas flowing into the cylinders, it's going to reduce the temperatures. You're effectively going to back off and lower your compression ratio further and bring your temperature down to within reason. So how does that work? Well, here we've got an example, and the arrow is going to appear in the wrong spot. Here is the demand cooling control module on a Copeland. So you see this little, looks like an oil fail with a big red button on the front of it. That right there is what manages and controls when we start injecting, when we want to start adding refrigerant. So this bullet point is in the wrong spot. It's actually pointing to the high pressure control. I don't know if you guys can see my mouse hovering over here, but it's the sensor is actually this small little silver hex directly in the front center of the cylinder head. The temp sensor there it protrudes into the cylinder head about 2.5 inches or so, and that samples the temperature that the Copeland happens to have found that is the most ideal location to manage and measure the cylinder head temperature and determine when we need to start injecting liquid refrigerant. So the demand cooling injection valve here that you see on the side of the compressor is nothing more than a liquid line solenoid with a metered orifice. So when it's open, it can only blow a specific amount of refrigerant in. It's not like it's dumping a full 3/8 inch flow of liquid in there. It's actually just spraying a small amount of liquid mist into the compressor, and it just injects it right directly into the suction pass of the suction port inside the casting of the compressor. So by doing so in the spot that it does it, we don't flood the motor, we don't do anything to spray oil, spray refrigerant directly onto the windings of the compressor. Rather, we shoot it directly in there onto the walls of the cylinders, which are usually quite hot, and therefore that pretty much ensures that no liquid, droplets of liquid or any sort of liquid is actually going to reach the valve plate. And then different, obviously different compressor formats have this liquid injection in different spots. There are a few several manufacturers, several applications where they do inject it directly into the suction line near the back of the compressor, but just be aware of the format, whatever it is that you're working on and looking at. Another thing to point out here that we didn't discuss in here, if you look at the top of this picture, you can just barely see the bottom of the head cooling fan. So also and you'll see it frequently in the R22 low temp applications, but you'll also see it in the 507 or 502 based low temp application. There's a fan that actually blows air down onto the cylinder head, and that aids in cylinder head temperature control by keeping the casting a bit cooler. So it's kind of a little preemptive way to keep the cylinder head cooler without inducing the need for liquid injection. Since liquid injection adds load to the compressor without actually doing anything for the operation of the rack, it's very inefficient as far as you're wasting an awful lot of energy by inducing a false load onto the compressors. But it's really unless you have something that can slow the compressor down like a VFD, liquid injection is really the only thing you can do for high temperature scenarios, and the compression ratio scenarios that you run into. So there's a few things that that are industry standard that are done to help curb the high temperatures that we see, especially in the low temp applications. So let's move into capacity control on a rack where you have parallel compression, parallel racks. What you see mostly in supermarkets, where you actually turn compressors on and off as load increases and decreases. So to maintain your suction pressures, when your suction pressures drop down and the store closes and pulls curtains and you just don't have the load, you obviously don't need all the compressors that you have when it's under the full load conditions. So you have low pressure controls that are actually going to cycle compressors on and off. Here's a picture of an old little Hussmann rack with some Bitzer compressors on it. So we got 4 pumps, 4 compressors on it. All your different suction loads come down from the top with your EPR valves on it. You can see. So this is just an example of a small parallel rack that you'll see in grocery stores. So you'll have suction sensors inside of the suction header. The header is common to all 4 pumps, all 4 compressors. The discharge is common to all 4 of them, so they all contribute to the same mass circuit load for the dynamic process of the refrigerant. So that pressure control is actually controlled mostly by a computer, and that pressure relative to the setup is going to determine what compressors are running as needed. So different control systems have different approaches on how they determine that and how they try and maintain the most stable suction results, but the effective process is all the same. They're just going to turn on and off compressors as needed. So the other way we can do that is instead of turning the compressors on and off completely, we can use variable frequency drives to slow compressors down. That effectively does the same thing, and instead of turning them off, we just slow them down or speed them up as needed. Here we can see just a picture of a VFD. Here we've got a compressor running at 48 hertz, which is 29% of its capacity. That's just yet another way of doing capacity control. 60 hertz for motor, for that would be full speed. There are several applications, like if you guys have ever worked on the Bitzer Speeds that you'll see, that's mostly a Costco, mostly you'll see in Costco, the Bitzer Speeds run all the way up to 87 hertz. So they're spinning pretty fast. It's a smaller pump, smaller compressor that moves a pretty good amount of gas through it with a small footprint. And then it'll run all the way down to, I think, 38 hertz or 40 hertz. So on full speed, it's spinning pretty fast. So again, lowering the frequency will slow the motor. The percentage there is the percentage of the torque for the motor drive. Here's another capacity control method. It shows VFD on a scroll compressor in the slide, but you're not really going to see VFDs too much on scroll compressors. You cannot, I don't know in this slideshow, there's no slide here showing the effect of the dynamic operation of a scroll compressor, but scrolls require kinetic inertia. They require the spinning inertia of those scrolls to seat the scrolls and effectively allow it to compress. So if you start slowing a scroll down too much, the scrolls can't seat against themselves and it effectively can't do any work. So generally on a scroll compressor, I'm sure you guys have all seen or heard of the digital scrolls. And a digital scroll has porting inside that actually uses gas to bypass portions of the scroll. So the motor spins a constant RPM, but it effectively unloads a portion of the scroll, just like we unload a portion of the cylinders in a reciprocating compressor. We do the same thing inside of a digital scroll. So rarely will you see a VFD or an inverter on a scroll compressor. Now you can do it to a percentage, to a point, especially on a single system where you have one compressor and one fixed load, and you only need to vary that capacity a small amount. So they are out there. You will see them, but the speed throttling range of a scroll compressor is nowhere near what it can be on a piston compressor, on a recip, or a screw compressor. Those types of compressors do not rely on gravity or inertial energy to do what they do. They have mechanical valves and means of moving gas, so they can throttle up and down and spin a lot faster, a lot slower than what a scroll can do. So here we show we could have up to a 60% capacity reduction. And a note here that it is used on heat pumps. So you'll see these on systems that are singular, just a single system. Very small throttling range, very fixed load range. I guess that was the last of the slides. So it's kind of a short session today. Does anybody have any questions about unloading or capacities, compression ratios?
I have a question.
Yeah.
So on the compressor, what happens if everything's satisfied and your compressor is still running? What components would that be?
That would, well, if everything's satisfied and you're not moving refrigerant, so your liquid line solenoids are all closed or suction stops, whatever means there are, then you would have a low pressure control that once that suction pressure reached a minimum, it's going to shut off the compressor and you're going to effectively stop all of the work it's doing. So you've got to have some sort of a safety means in there that will protect that compressor and prevent it from just sitting there running in a vacuum or running under those very low load conditions that will eventually just make it run so hot it'll burn itself out. So there'll be a low pressure control in there.
Right, but sometimes on some of those scrolls, there's been a few of them, and the compressor winds up being bad because obviously you can't rebuild the scroll. But
right, so on a scroll, remember, the scroll compressor cannot pump down. If the compression ratio gets too low, it no longer can seat its valves, or I mean, it doesn't have valves. It can know that scroll, that compliance scroll now cannot seat and effectively do any work. So when you get it down to where it's not moving much gas, what little of the scroll is compressing is basically not moving any gas through it. So it is doing some compression for part of its scroll cycle, but when there's not enough there for it to take the next gulp over, the next scroll to start and keep that going, it's just basically bouncing on itself. So you're doing partial compression, but it's not moving through the scroll. So it's just sitting there getting hotter and hotter and hotter and hotter. And remember earlier in the slides, we had mentioned that oil starts smoking or burning at around 300 degrees, depending on what type of oil you have. As that oil starts burning and that smoke is developing, you're building up carbon and broken down oil on those scrolls, which is added friction, and it adds a gummy, sticky mess inside of the compressor, and you're just going to start gumming it up. And then the compressor can't do its work, and it's just a downhill spiral into a catastrophic failure from that point. So when you get to a scroll and it's not pumping, it's probably because it's just gummed up the scroll, and the scroll can no longer seat because it burned itself out because it was running on low refrigerant, or it was pumped down and it couldn't ever shut off whilst in that low compression ratio scenario, or that super high compression ratio scenario. So that's effectively what will fry a scroll compressor. Does that make sense?
Yeah, thank you very much.
So let's see, any other questions like with demand cooling, or any of the other compression ratio management means that are used? So, well, I guess if we don't have any other questions, we'll just have kind of an early session. Again, I had to jump in and do this for Jim, so I apologize if it was running short or if you guys are expecting more. But hopefully that gave you guys a little bit more insight on some of the compression ratio management techniques and attributes throughout the industry.
Yeah, thank you, Scott.
Cool. All right, guys. Well, you guys all have a good rest of the week. Normally I do Friday stuff, so I won't say have a good weekend, but have a good weekend when it gets here. So we'll talk to you guys later on, and just reach out to me or Jim or your anybody to if you got any other further questions, feel free to give me a call. My phone is going through the porting thing today, so I don't know if it'll work, and I left my phone with Ty, who is now down in Blanding. So anyway, all right, guys, everybody be safe out there, and we'll see you at the next session.
Thanks.
Appreciate it.
Yes, sir. Sorry, it was kind of short.
No, you're good. No worries. I was a little bit into it, so.
And you can get the slideshow, watch the whole thing on the webs.
Thank you.
Welcome. Thank you, man.